access control. Okay, so just let me open access control. Okay, so now what is actually an access control? And you may have seen about this particular feature is available in data link layer. Okay, so in this particular case we are talking about everything inside a LAN, because we are talking about is our data link layer. Okay, so now what actually is access control and why do we need it? Okay, so there are actually two types of link in computer network that exist here. The first link is your point to point link and the second link is your broadcast link. Okay, so in point to point link, there is only one link between a sender and a receiver. You already know this. Okay, so if it depends upon the mode of communication, either the channel is full duplex, half duplex, or a simplex one. Okay, so actually the link lies between uh, a sender and a receiver, and in this particular link there is no problem. Okay, so because the link only communicate the communication only between two particular stations are taking place, there is no problem in point to point link. It can happen, there is no problem in that. But what is the problem in broadcast link? Okay, so broadcast link means on one link there are multiple stations placed. Okay, so now what will be the problem if suppose a station wants to send something to this particular station, that is your D station. Now D station wants something to transmit to A station. So what can happen is that at both a similar time like 11 a.m. they both starts transmitting the data. Okay, so at some time between there might be a collision between these two particular entities here. So if this is a packet, this is a packet from A side, this is a packet from D side, a collision might happen. Okay, so if I want, because we are broadcasting the signal, it means that every station on the way can can see this particular signal, but it cannot just read the contents of the message, because we already know that it matches the destination, the packet, the frame with the destination network. If the destination network is equal to if a station is reading the packet and if it finds that the destination network is equal to itself, so then it tries to reads the message or contents of the message. Okay, so that is why the packet is broadcasted here and here. Okay, so when it is broadcasted, it means every station on the way can see that there is a packet going, but only the destination station can read the content of the message. We already know this. I have already discussed in data link layer in framing also. Okay, so now when if you're seeing here, I want I want some technique such that there will be less collisions or no collision, something like that. I want to control the access of every station. So I want to limit the access of every station such that the stations should not send the packets at the same amount of times. So the such that there is no collision. Okay, so if they send the packet at similar time, there will be very high chances of collision. If they do not send if one station is sending some data and another station is refrained from sending because one station is sending it, there might not be a collision. Okay, so access control is that technique. It's that technique that that says we want to avoid collision in a multiple access stations. Okay, so if every station have access to a similar channel, so we want to avoid that thing. Okay, so that is why access control exists. Okay, so if you see in point to point link,
Sir,
point to point, yes, yes.
sir, can you please send the link for the meeting again in the RSVP form, sir? Because many of the students are not getting the link and that's why they are not able to join the lecture.
Okay, so you are not able to share the same link with everybody.
Sir, actually it is removed from the calendar so they are not able to join it. So sir, if you will send the RSVP again, then maybe they will able to join.
Okay, okay. Just
Tell
let
them to check from the team, not calendar.
wait for a second. I tried to again send it. But why someone is getting it, somebody is not? Just let me check. Just wait for a second.
Sir, in between the week, there was one day when the RSVP was been cancelled, and that
Okay.
time it was removed from the calendar, sir. That's why.
Okay. Okay. So I'll just share the link on the. Okay. So I'll on the email. I think I can do that. Mm, Just wait a second. I have to wait. Check for it. Just wait a second. Okay, what I can do is because I have to look for email of every individual group, I have sent the invitation or joining a link in your chat box. You can do. What can you do if you have any WhatsApp group or your BRs, if anybody BR is here, so they can just copy and paste this link to every group itself. Okay, so I have to look for each and every individual mail, so that will take a little bit of amount of time because I haven't uh, set. I have to check it. Okay, so what you can do, I have sent you the link in your chat box, so you just copy and paste it. I will see in the next meeting what actually is the problem here. I'll again try to add a sub. I will cancel this meeting and will again add the same meeting. Okay, so I can do that.
Okay, sir.
So okay. Okay, so just let me again share the screen. Okay, so because actually 106 people have accepted the invitation, I think that might be a problem. Okay, so I'll again revise the meeting. Okay, so in point to point link, what is happening in point to point link? I already said to that there is on not a problem because in point to point link there is only one sender and one station, and there are only two stations. One will be sender, one will be receiver. If the link is full duplex, it might be that both can send and receive. There is no problem in that. Okay, so point to point is a dedicated link between two stations. The entire capacity of the link is used for the transmission of two connected stations, depending of the type of channel. So type of channel can be half duplex, full duplex, and simplex. The data flow can take split between two stations. Okay, there is no problem in that, but the problem will be in broadcast link. Okay, so broadcast link is a common link to which multiple stations are connected, and the capacity of this link is shared among connected station for transmission. Okay, so there might be chances of collision that the same because if you're seeing here one station, two stations, suppose there are four stations, and suppose at 11 a.m. every station tries to send a message. Every station tries to send broadcast a message. Okay, so if it broadcast a message, it will definitely will be collided with other transmission or other workstation transmission. So that is the problem when we come in terms of broadcast link. So that is why access control is there. So access control is a mechanism that controls the access of station. So it definitely controls the access of the station so that for a particular amount of time a workstation will got access. Okay, so at a particular amount of time only one workstation will got access to the link such that it will transmit the data and no other is transmitting on the same time, so that way you can avoid the collision. Okay, so broadcast link require, so broadcast link is in mostly these cases, in broadcast link the access control mechanism is implemented. This is because the link is shared among several sessions. Okay, so access control is further divided into many techniques. There are 5 techniques, I think. Okay, so why we need access control? To prevent the occurrence of collision, or if the collision occurs, how to deal with it. Okay, so access control is a mechanism. It tries to prevent a collision between two stations, 2 or 3 station or 4 station. It tries to prevent it, but it also gives you a fail safe mechanism. Okay, so it also tells you that in case if the packets are collided, then what to do. Okay, so this particular access control guarantees that after collision also how to deal with it. It also provides that mechanism. Okay, so consider a situation that it will show you the situation in the next one. This is the example of it. It is saying that from this one packet is coming, from this one a packet is coming at the same time. There might be a collision here. Okay, so here two stations A and D are transmitting their packet data simultaneously. This situation give rise to a collision between the data packets transmitted by them. Thus, to prevent the collision or deal with it, access control is needed. Okay, so actually it is divided into these many techniques, that is time division, multiplexing, polling, CSMACD, token passing, and aloha and slotted aloha that comes in which. Okay, so time division multiplexing is the simplest approach. So after time division multiplexing, there are some disadvantage of it. So to avoid the disadvantage, we use polling. Okay, so actually the polling is the similar technique as time division multiplexing, but just we added some extra feature to recover from the disadvantage that we face in time division multiplexing. Okay, in a similar way, what disadvantage we face in polling, then we invented another technique, that is CSMACD. Okay, so everything that I will discuss, it will be logical and it will be step by step. Okay, so I'll tell you that what are the exact problems that we face. So that is why we switch on to this particular technique. Okay, so the first technique is your time division multiplexing. Okay, so just let me uh, open the time division multiplexing. Okay, this one. So see, in time division multiplexing, what happens is that it is already in the game. It is already in the name. Sorry. Now, if there are multiple stations here, suppose there are multiple stations, one, two. Suppose there are 4 stations. Okay, the name of the station is 1, 2, 3, 4. And now, what exactly how this time division multiplex work? It will assign. It will divide the time in a round robin manner. Okay, so it will divide the time. Suppose it is dividing the time. At this time, only one workstation can have access to this particular channel or this wire or this link. Okay, so this is link or channel or wire or anything. Okay, so or medium also. Okay, so if I am using the same thing, I'm using the same if I'm using either of these 4 terms, actually I just mean it, that these 4 terms interchangeably can be used. Okay, so link, channel, wire or medium is one and the same thing. Okay, so at this particular time, so I have divided the time into slots. Okay, so this at this particular time slots, this will be some time. At this time slot, only one can access the link, no other can access the link. Okay, so if 4 wants to send a message, it will not send it because the time for sending the message is denoted to this workstation. Okay, in the similar way, at similar amount of time, after this time is over, the time will be given to 2 and then 3 and then 4. After the four stations have been given assigned time, and then again it will be given to 1, then 2 and then 3 and then 4. Okay, so this is called your round robin manner. Okay, so round robin manner, it means that when a complete cycle is completed from one round for one round, after that another the same round will be conducted, that is 1, 2, 3, 4. Okay, so when how this time division multiplexing works, so we want that there should be no collision between the workstation. Why the collision is happening? Because at the same time, one or more workstations are transmitting or sending or propagating the data. Okay, so that I do not want that. So I got to the simple solution. The simple solution is, what I do, I'll divide the time into different slots. At a particular slot, one workstation will be allowed to transmit the data or to send the data from one station to another. Okay, so everybody will follow that particular time slot. Okay, so now it is given the same way. So time of the link is divided into fixed size interval called time slots or time slices. Okay, it's one and the same thing. Time slots are allocated to the station in a robin round or round robin manner. Okay, so in if you are from computer science background, you may have heard about this particular word in operating system. Okay, so in scheduling of task, we use robin round algorithm or round robin algorithm. You may have heard about this, but actually I already told you the meaning of this. Okay, so each station transmits its data during the time slot allocated to it. So every station, whenever the slot comes, only that station will be able to transmit the data, or it will be able to send the data. No other workstation will be allowed to send it. Okay, so in case station does not have any data to send, its time slot goes waste. Okay, so that is the disadvantage. Okay, so now what is the disadvantage here? Suppose now there are four workstations. Now I have divided the slots like this. Okay, so at one at when the time slot is given to one is sending some data, and when the time slot is given to two, so two does not have any data to send for. So this particular time slot is wasted. Suppose three also does not have any data sent and four also does not have any data sent, but one again wants to send the data. Okay, so see here in this particular scenario, the one has to wait for 3 into this time slot to get its turn. Okay, so whatever is the time slot, whatever is the time here, suppose I say ti is the time here. So one has to wait 3 into ti to get its turn, but others are not sending any data because they do not have any data to send. Okay, so this is the wastage here. You are seeing here for 3 into ti, this is the wastage that I do not want. Okay, so this is the disadvantage. Now what the burning question will be, how much is this time? Okay, so how the time slot is decided. Okay, so now if you're seeing here, this is the example that I've already given you, that it is assigned in a round robin manner, a b c d, then again a b c d and so on. Okay, so now again, how do you decide the size of the time slot? Okay, so what actually is the time slot? Okay, so now if you think, suppose we'll just take a simple step here. But actually, the size of the time slot is given to as TT plus TP here. So I have to tell you that how can you say that it is the time. Okay, so suppose you are at this particular station, and this there are many stations there. Okay, so you are one and you want to send your data to 4, suppose it. Okay, so how much time did you will require, how much time this workstation will require? So this workstation will require to put the packet onto the link, and whatever is the propagation delay to reach at the uh, workstation. Okay, so the time slot will also be the total time that is taken for this whole process. Okay, so the time slot, that is why is tt plus tp. Okay, because in this much amount of time you will be able to transmit the data, you will be able to put the packet onto the link, as well as you will be able to successfully transfer all the bits that you want to send. Okay, so at this much amount of time is definitely required for a time slot. So every time slot is based on that. Again, there is an assumption here. Assumption is that for every assumption here is that tt is equal. Tt is equal for every workstation here. Okay, so tt means that actually the to put the packet onto the link, every workstation require same amount of time. So it means that the length of the tap packet is fixed here. So that is one assumption that I've taken. So it is taken here. So for in order for easy calculation, okay, length of the packet here is fixed. It means if every packet length, uh, this is just an assumption when I'm calculating this formula, that the size of time slot will be tt plus tp, when I'm assuming that every packet has the similar length. Okay, so just keep in mind this assumption. Okay, So now if you see here, the size of each slot is kept that each station gets sufficient time for the following task. The following task is to put the packet onto the transmission link. So this much amount of time will be required. Last bit of the data to get out of the transmission link. So this much, that last bit of the data means propagation delay. Okay. So thus the size of the slot is maximum it is taking as TT plus TP here. Okay. So again, there is a assumption here. So most of the time, many students just many people just forget about this, that there is assumptions. That is why I've included this particular assumption in the PPT, that to keep the size slot constant, we have to assume that all the station want to send the packet of same size. Okay, so this is the assumption here. So that is how this formula is applicable. If every station has different packet size, then the formula will differ. But again, I'm only considering just the assumption is just all the packet length is same. Okay, so it can be done by just assigning a fixed length packet or to every workstation as well. Okay, so this keeps TT constant for all station. So we have considered the worst case where both the stations are present at two extreme ends. Okay, so this particular time is applicable for the worst case, because if you see in the diagram that I've drawn here, so when these two extra stations want to communicate, so TP will be maximum. Okay, so that is why they have taken the worst case here. So it means that if you want to communicate with the third station here, the TP will get less. Okay, so why? Because the distance between 1 and 3 is less than the distance between 1 and 4. Okay, so that is why the worst case is considered for figuring out a formula here. Okay, so one assumption is also there, that TD is constant, so that you keep in mind. Okay, so this ensure PP will be maximum and all the station will get the maximum or sufficient time to propagate their data. Okay, so the time slot we know about it now. How this time slot will be? So the time slot here will be TT plus TP. Okay, keep in mind every time the time slot will be TT plus TP. Okay, so if I want to find the efficiency now, okay, so how can you find the efficiency of this particular TDM? Okay, so I'll say what is the efficiency of TDM. Okay, so efficiency, you already know what will be the efficiency. It will be the useful time over the cycle time or the total time. Okay, so it is one and the same thing. So useful time, what exactly is the useful time here? Useful time, if you think that from this was the scenario here. In this scenario, I'm putting the packet onto the link, so that is my TT, and the data is transferred to this data is transferred from this station to this station. Okay, so actually if you're seeing here, for TT plus TP amount of data, the station is doing some work only in this amount of time. Okay, so because in TP time the station was not doing anything, so TP is just the time taken for one the last bit to reach to the destination station. So actually the workstation is not participating in this TP, because actually if you put the data onto the link, it will eventually get transferred to it. The station is only transmitting the taking participation in this particular time, because it is a responsibility of the station to put the packet onto the link. So the useful time, it means that the time in which the station is doing something is TT, and the total time will be your TT plus TP. Okay, so out of TT plus TP, the station is doing some useful work in TT amount of time. Okay, so in a similar way, you can find the effective bandwidth or throughput. It is one and the same thing. So effective bandwidth will be efficiency into bandwidth. You already know about this. Okay, so this is the same formula, and you can find it out the effective efficiency. Okay, so if you want to take example as well, so you can take example that if suppose TT is 1 millisecond and TP is 1 millisecond. So what is the efficiency here? Okay, so efficiency in case of TDM. Okay, so I think I have given the formula till here. So again, you can simplify it to 1 over 1 plus 2a. So it is TT over TT plus TP here. So divide and multiply by TT here. So it will get if you divide the numerator and denominator by TT, so divide and multiply by TT. Okay, so it will be 1 over TT, 1 over 1 plus TP over TT. Okay, so it will be 1 over 1 plus A, where A is TP by TT. Okay, so if you want to find out, you can do either you can directly put the value here, it is also fine. So TP is 1 millisecond over 1 millisecond plus 1 millisecond. So it will be 1 by 2 here, and it will be 50% efficiency. If you're seeing here why it is 50% efficiency, because the station is doing work for 1 millisecond out of the total 2 milliseconds. So that is why the efficiency is 50%, because in TP the station is not participating. Only the station will participate in only putting the packet onto the link. After that, the packet goes towards the other end. In that particular work, the station has no matlab, it has no participation in that. Okay, so you already know what will be the disadvantage here. Okay, so the disadvantage here is that when, okay, so I think I'll go to the next slide here. So disadvantage here is that if any station does not have any data to send during its time slot, then this time slot goes waste. Okay, so this particular thing reduce the efficiency here. So how can you that this time slot could have been allotted to some other station that are willing to send the data. Okay, so if I take the same example, that there are 4 workstations. Suppose in this workstation, A1 has some data to send, 2 does not have any data to send, 3 does not have any data to send, and 4 does not have any data to send. But 1 has the data to send, but again it has to wait for this much amount of time to send the data again. So what is this time here? That is your TT plus TP here. Okay, so 1 has to again wait for 3 into TT plus TP amount of time to send the data again, and this much amount of time is wasted if I assume that 2 does not have any data to send, 3 does not have any data to send, and 4 does not have any data to send. So that is the main disadvantage here, that there is lot of wastage here. Okay, so this time slot could have been allotted to some other station willing to send the data, but it is not allotted because the time slot is assigned in a round robin manner. So I cannot skip any other station. So that is the main disadvantage of this technique. So in this particular technique, I have added something called polling. Okay, so that is your next access control technique, that is polling. So what I'll do before assigning, now we are not following any reservation system here. So we are not reserving we are not reserving any time for every station. So what we'll do, before sending the data, the the this access control method takes a pool. Okay, so there are 1 2 3 4 stations. Suppose there are 4 stations, so out of 4 station, it decides, it takes a poll that which particular packet wants to send, which particular station wants to send the data. After taking a poll, it will assign the time slot based on the polling algorithm. Okay, so it means that whoever have won the poll, whoever won the poll will get its time to transmit the data. So there is no fixed system, there is no reservation system. We will not reserve any time slot. It will be decided on the polling algorithm. Okay, so there is no need to go detail into the polling algorithm. So it's simple. If you want to go it, you can look for it, but there is no need for access for this access control method. Okay, so a polling is conducted in which all the stations that are willing to send the data participates. Okay, so from the polling algorithm, so it's a simple algorithm. It just decide that which particular station will get its chance based on this algorithm. Okay, so when the polling algorithm is run, it chooses one of the station to send the data. Okay, so in this polling algorithm, you have to know that if suppose if 1 and 3, okay, so if 1 and 3 wants to send the data, both of them has a equal probability of sending the data. Okay, so both of them has a equal probability of sending the data. Keep that in mind. Okay, so in polling algorithm, if any station, if there are 3 stations that want to send the data, the choice of getting what you say, the probability of getting any station chosen is equal. Okay, suppose I'll say that in there are 4 stations out of 3, 4 stations out of 3 want to send the data. Okay, so the probability that 1 will be chosen is equal, the probability that 2 will be chosen will be equal, and the probability that 3 will be chosen is also equal. Okay, so whatever is the probability, the chance of getting any one of these 3 selected is similar. Okay, so if like if you are uh, if you're tossing a coin, the probability of head and tail is equal. So either 50% it will be head and 50% it will be tail. In a similar way, the probability of choosing these three, this one out of these three is equal here. Keep that thing in mind. Okay. So now the chosen station send the data to the destination. So suppose I've taken the second one, but after the chosen station has sent the data, the cycle will repeat. Okay. So again it will take a poll. It will again take, suppose I have chosen this particular station here that 2 wants to send the data. After that 2 again wants to send the data. Again there will be, suppose I will again take a poll, and from the polling algorithm everybody has the similar probability. So again if 2 is chosen, so that is not fair. If you see that because everybody is getting the same probability, so it can happen that in first time 2 is chosen, second time 2 is chosen, third time also 2 is chosen, fourth, fifth, sixth time it can happen because everybody has the same probability. Okay, so
Sir,
that, yes, yes.
sir, will the priority of their work won't matter?
What?
Will the priority of their work won't matter? Like
No, it
priority
will
is
not. It will not matter.
okay,
Okay.
sir.
So why it does not matter? Because every station is sending the data. Okay, so they are not assigning any priority to data. It in operating system it is different, because in operating system there are some important things. So that is why there is priority scheduling. But in computer networking there is nothing like that. Okay. So now see what again the example here. Now if you want to, what will be the time slot now? Okay, so if you find the time slot now, so in this time slot you already know there will be tt and there will be tp, and now there is one thing more added here, that is t poll. So the amount of time you have taken for polling. Okay, so that will also be added in your time slot. Okay, so now your time slot will become, if I take the time slot, it will be t poll plus TT plus TP here. Okay, so in this I think they are given T send here. The T send here actually means is TT plus TP here. Okay, so now if you find out the efficiency of TDM with polling, it will be different here. Okay, so why? It will be again the useful time over cycle time. Okay, so what exactly is the useful time? Useful time that a particular station is doing something useful. So a particular station will be doing something useful when it is putting the data onto the link, only this amount of time. So I'm taking TT, and what is the cycle time here? Cycle time or your total time will be T pole plus TT plus TP. Okay, so this is the efficiency of your TDM with polling algorithm. Okay, keep in mind throughput or the efficiency or throughput or the effective bandwidth will again the formula is same. The throughput formula is efficiency into bandwidth. Okay, so we already know about this. Okay, so there is no change in that. I am only talking about efficiency here. Okay, so the efficiency formula can change depending upon the depending upon the transmission or what we are doing here. Okay, so now the most popular, okay, so there are some advantages to this one. So unlike in time division multiplexing, so no slot is wasted here, so that is one advantage. And second advantage is because it increases the efficiency as well as bandwidth utilization. Okay, so that is because no slot is getting wasted, so you do not have to wait for some amount of time. If you do not want to transmit the data, you will not be given a slot. But again, the disadvantage here that I've given you, that there are few station might starve for sending the data. Okay, so again I'm, because every station have a equal probability for selecting. So suppose in the first go this particular station is selected. After that 2 again wants to send the data, 1 to 3 again wants to send, because 1 and 3 will all, because obviously we sending the data, they obviously be wanting to send the data because in the previous one 2 was chosen. Okay, so again 2 wants to send out the data, so there will be again it will be random draw from 1 2 and 3 again. So 2 is chosen again. If again 2 wants to send that data, again 2 will be chosen. Okay, so that is why it's saying few station like this one and this will might starve for sending the data. They will never get a chance. Okay, so I'll show you something called a back off algorithm. So I'll show you in this particular algorithm how if a station won if a station won the first probability, that if suppose in this particular case 2 has won, the probability that it will again get the station will get increase in the second time. Again, if it is selected second time, the probability it will be gotten chosen for the third time will get increased. Okay, so I'll show you this particular thing in back of algorithm. So just wait for a second. When I get to back of algorithm, I'll show you. Okay, so that is why this is the main disadvantage. The another disadvantage is that t pole is added here. Okay, so previously it was only tt plus tp, but in this the whole slot was t plus tp plus t pole here. So this particular amount is wasted. I don't call it wasted, but still it is taking a little more time than the previous one. But if 1 2 3 4 stations, they all want to send the data, then your TDM is better approach. But if 1 2 3 4 out of these two, only two station want to send of the data, then TDM with polling is more better approach. Okay, so that is the usability. Okay, so actually this is the better approach, because all the time all the stations might not want to send data. Okay, so that is why this TDM with polling considered as a better approach, but it has some disadvantage. Okay, so link sharing, if you are seeing here, it is not fair, since each station has the equal probability of winning in each round. So that is the main disadvantage of it. Okay, so now again in to get out of it, we have another access control method, that is your third access control method, that is CSMACD, and it is one of the most popular method that is readily employed in your Ethernet. Okay, CSMACD, the full form of it is Carrier Sense Multiple Access Collision Detection. Okay, so now you understand this term. It's very important here. So CSMACD is readily or most widely employed in Ethernet. Okay, so many times they will not use CSMACD term, they use Ethernet terms. Okay, but actually this access control method is employed in Ethernet. So they both of these terms are used interchangeably. Okay, so keep that thing in mind. Okay, so now it is one of the most important access control method now. So now what exactly is the disadvantage in the previous one, that the polling time is required, as well that there is no, what you say, fair share. Okay, so the probability to share the access channel is not fair, because everybody is getting the same probability. Okay, so now you see what is Carrier Sense. So in, suppose there are many workstation here. Carrier Sense means that this particular station, suppose I am calling it ABCD, this particular station can sense the channel or sense the carrier. Now this particular wire is also referred to as carrier or wire or medium or link. Okay, so everything is interchangeably can be used. Okay, so this particular station has the capability to sense this carrier, that is your link, and this particular carrier will be multiple access. It means there will be multiple station that can be accessing this carrier. And now there is a collision detection here. Now this is the feature of this CSMACD. Now why is this collision detection? Now suppose I'll get to this particular part later. Just I'm as getting this particular part. Okay, so now it is saying that this workstation A has the capability to access this carrier to see if there is any communication going on this carrier. Okay, so this is the advantage, that this particular workstation can access the wire and see if there is communication going on. And if there is communication going on, it will not send it packet, it will wait for the communication to be over. After some time it will again access this carrier to see that any kind of communication is going on. If there no communication is going on, it will be ready to send its data. So that is the advantage of it. So you may be thinking that in this particular scenario there will be no collision. So actually it is sensing the carrier before sending the data, but actually there will be a collision, because the station can only access this much area. This station can only access to the point that it is connected. So only this particular position it can sense the carrier. It cannot sense the whole wire. It cannot sense the whole wire if there is communication going on. It can only sense this particular area to which it is connected to. So this particular workstation can only access this or can only sense this much amount of area, this much amount of area, this much amount of area. Okay, so suppose if there is some communication from D is coming and A tries to sense the carrier at some time, and it will find that there is no communication going on because the communication is still here. So it actually if you're seeing here the this particular link is not empty, it is transmitting something, but this particular A will think that the link is empty because it can only sense this much amount of area. So when it finds the area empty, it will tries to send its own packet, and then there will absolutely be a collision. Okay, so that is now the second term comes in picture, that is collision detection. Now it is providing you a solution to detect the collision. Now why there is a need for collision detection? Because in data link layer we are transferring the data in LAN, that is in data link layer, and in LAN there is no acknowledgement whatsoever. Okay, so whatever algorithm you are seeing here in LAN which there is no acknowledgement, actually there is no acknowledgement. So that is why I have to detect there is if there is a collision there. So only way of knowing a collision detection, they have given approach to detect a collision. I will tell you. I will also tell you why is this particular formula is given. So don't worry about that part. Okay. So in LAN, when you are transferring in Ethernet or some other algorithms, you may have heard about this, or there is no acknowledgement, because in LAN always the transmission is considered to be very reliable. So we do not use any kind of acknowledgement in that. Okay, so if you want to send the data across networks, okay, so from in internets, that is where we definitely try to get some acknowledgement. Okay, so that is why CSMA CD is mostly employed in this particular scenario, that where you want a collision detection as well. Okay, so if there is a collision, you want to detect it so that you can again retransmit the data. Okay, so if you know that your data is in a collision, so it means that it will get corrupted. So you definitely want to detect that and again want to send the same data so that it will not get corrupted. Okay, so now the first step here is sensing the carrier, that is any station that is willing to transmit the data. Sense the carrier. If it finds the carrier free, it's transmitting its data packet, otherwise not. Okay, so that is simple. Now how each station can sense the carrier at only its point of contact. Okay, so that is the main disadvantage. If it is able to detect the whole career, it can only sense the whole career, then there will be no problem. But it is only able to sense the career at a point of contact. It is not possible for any station to sense the entire career. Thus there is a huge responsibility or huge possibility that a station might sense the career free even when actually it is not. Okay, so I've shown you this example. Actually the station was not free because D is transmitting the data, but at one time when A senses the carrier, at this point it is showing that there is no transmission going on. Okay, so that is the disadvantage. Now it can happen. So for that we have to do something called a collision detection. Okay, so now if you see here at this current instant, it is giving the same example here. If A station senses the carrier at the point of contact here, then it will find a carrier free. Okay, so this will find the carrier free. Actually this D station has transmitted the data, but the carrier is actually not free because D is already transmitting its data. Okay, so if station A start transmitting its data now, then it might lead to a collision with the data transmitted by the station D. Okay, so keep in mind how can you detect the station. Now this becomes our next question, that is how can we detect the collision. Okay, so here with this particular formula that is given, that your transmission delay, that is TT, should be greater than equal to 2 into TP. If you set this condition, then you might be able to detect the collision. Okay, so I'll show you what actually is the meaning of this formula. It's very important, so understand this particular thing. It's very important to understand how is this formula come into existence. Okay, so now I'll take an example. Now why this particular formula, which why is this, what is the foundation of this formula? Okay, so now suppose now you already know that from A station, suppose this is station B. Now you have sensed the carrier, it is empty. You have sensed the carrier, it is empty, and you tries to send the message. Okay, you try to send the message, and at some time of amount of time there will be a collision. Okay, so when there is a collision, the collision signal, keep in mind, will be different from the data packets. The collision signal will be high in frequency. Okay, so that another station will easily get to know that there is a collision. Okay, so the collision signal is a bit different, higher in amplitude, so that every station can recognize that there is a collision. Okay, so now the main question is, how does A knows about the collision, okay, so because the this is the main question here. Okay, so because the A's packet is involved in the collision, such that if A knows about the collision, so it will be able to send the data again. So that is the main concern here. Okay, so we do not use acknowledgement in LAN. So how can it be? Okay, so the main underlying concept, understand this, that is A should receive, so I'll write it, it will be more clear. A should receive the collision signal. A should receive the collision signal. This is the main foundation of the formula. A should receive the collision signal when it is still transmitting the data. Okay, so what is the meaning of this? Okay, so its meaning is, suppose A is putting the packet onto the link, and that whatever is putting it, so it is directly going towards B. Okay, so now I want, if there is a collision, I want that the collision signal will come back to A. Now A will know that the my packet is included in the collision if A was still transmitting the packet and receives the signal, collision signal. Okay, so that is the only way that A will know that my packet, that the packet that I'm sending is involved in the collision. So that is how, this is the particular foundational statement that we know, that we used to know that a particular packet is involved in a collision. So okay, so now how can you can, if I take it into simple terms. Okay, so like suppose if your packet is so much large, so if I say if my packet is so much big, this is the packet, suppose my packet is so much big, like this particular packet. Okay, so at the front one is sending some data, so from B is also there is some, that is packet that is very large here. Okay, so now at this particular amount of time there will be a collision. Okay, so now A is still transmitting the data. Now if you're saying here A is still transmitting the data, but actually A also got the collision signal back. Now A will, in the similar way, B is still transmitting the data, but B will got the collision signal back. Okay, so by this they will know that it is our own packet that is involved in the collision. Okay, so suppose I'll take a simple example, that is TP. Suppose TP, that is to transfer the data from the sender to the receiver, total time that is taken by is 1 hour. Okay, so at time, suppose 11 a.m. both start sense the carrier and find that the carrier is free, and they start transmitting the data. So, okay, so A and B starts transmitting. Okay, so now at time, so because both have because the TP is 1 hour and both of them are started the same time, so when they will arrive at here, that will be 30 minutes from this side, 30 minutes from this side. Okay, so at, I can say that 11:30, so at 11:30 there will be a collision between A and B, so I can see that directly. Okay, so now it means that at now how when does A and B will get the collision signal back. Okay, so at 11 the communication started from both hand. Okay, so at 11:30 the collision occur here. Okay, so now 30 minutes of time will also be required to get back here. So this collision signal will require 30 minutes of time to get back from this side and 30 minutes of time to get back from this side as well. Okay, so it means at 12. Okay, so at 12 both A and B, both A and B will get their collision signal. Okay, so we'll see their collision signal. Okay, so now I want at 11 at 12 p.m. I still want that A should be transmitting the data such that it can detect my own packet is included in the collision. Okay, so I want that my TT should be greater than TP. So this is the thing I want, that much amount of time. At that thing I only know that. How big of TP I do not know, but I want my TT should be greater than TP. I absolutely know with one thing that my TP should be greater than TT. Okay, so if I take the average case, this, if you are seeing here, this is the average case because I'll show you the worst case here. So if I show you the worst case here, worst case will be, okay, so I'll show you in the next one because I do not want to leave this one in the middle. Okay, okay, so I'll see what is the problem with the invite. I'll again start the invite.